So let's take a look now to the properties of light, like the sunlight that we see or any light that we have seen in our life. And then we will move to phenomena like reflection, refraction, and so on. So when we see a light that is emitted from a source of some kind, let's say sun is the main source, okay, stars, television, bulbs, light that we see in our home, then the our eye receives only a small part of the light emitted from the source, not the whole thing, because light in the source is emitted into different all ways and forms. Okay. We also see the light that is reflected from an object of some kind. Let's say pencil. If we put pencil into the table, then we see the reflection of the light by this object. And light can it's assumed, is accepted that light travels in a straight line, and the evidence for this is that light creates shadows and it does not appear to bend around corners. Lights obey the law of geometry, and we will see the second part of the video will be in terms of the optic geometry. This is how it is known. And in a specific medium, light has a constant speed. And in vacuum or in air, it's considered to have a speed of 3.0 times 10 to the power of 8 meters per second. But when it moves to another medium, let's say water, diamond, or anything, then we'll have a different speed that is lower than the speed of light in vacuum, but will be constant through that medium. Okay, so let's see now what do we mean by all those properties that we mentioned. Let's suppose that we have a tree. So we have a tree here. And we don't know what is the height of the tree. However, what do we do in order to figure out what is the height of the tree is we put a meter stick at a certain distance, perpendicular with the ground, and then we measure this one here, and let's suppose that for our purposes this is 0.75 meters. And we measure on the other side, we measure the distance from where we are at to the bottom of the tree. And let's say that this is 17 meters. And then this being a meter stick, then we'll see how we can figure out the height of the meter. So now what we are dealing here is that it is known as the similar triangles. So triangle, the small triangle here, and I will just put some letters here, A, B, C, D, E. So triangle ABC is similar to triangle ADE. And when we are dealing with similar triangle, the related ratios are the same. So we saw that this is a meter stick, so 1 meter. And then what we have is AC over BC is the same ratio as AE over DE. And on all this relationship here, we know everything but DE, that is the height of the tree. So this will be 0.75 over, this is 1 meter, and they are all meters, is equal to AE, not AC, AE, that is 17 meters over X. So now what we have is just a ratio, but we cross multiply two that we know. So 17 meters times 1 meter over 0, divide by what is left. So meters and meters is cancelled out, and then we will have that the height is 22.67 meters, the height of the tree. Okay. So this is showing us that the light is following that is known as the law of geometry. Or if we have a pinhole camera, that pinhole cameras are just made by a black box where a small pin-sized hole is made in one end, and it is allowing the light to enter into that. And let's suppose that now we have like a person here, and we know that this person is, let's say, 1 meter and 62 centimeters, and then here we have a pinhole camera. So the hole is here, and then what we will see is, excuse me about my drawing. So the light will enter on this direction, and then we will see the image created will be inverted like this. And now let's figure out what is the height of the image created, knowing that here we have, let's say, 15 meters, and here we have the distance from the hole of the pinhole camera to the person is 12 meters. And let's figure out what is this X here. Again, I will put some letters so that A, B, C, D, E. And then what we have here is triangle ABC is similar to triangle CDE. And on that case, AB, the ratios AB over DE is the same as the distance between AC, AB is to CB, and EC. And after we plot the information that we have here, so AB is 1.62 over D is X equals to CB, that is 12 meters over 0.15. We can solve for X, so that's 0.15 times 1.62 over 12. And we will find the image, and then as you see here, the image is inverted. So 0.15 times 1.62 by 12. So it will be 0.0225 meters, and it is inverted. Okay. Now, to calculate the speed of light, it was very intriguing, but it's starting from Galileo, but then the one that actually figured out that a good way to measure the speed of light is Michelson. So Michelson, I will bring a picture of the experiment. So this is pretty much the experiment that Michelson did to measure the speed of light. So here we have a sided mirror, and the sided mirror that we have here is with 8, so 8 sides. And what was happening, so as soon as the sun was coming from Mount Wilson, was hitting one of the sides, and then in another Mount Baldy, there were 35 kilometers away, there were some stationary reflective mirrors. And here, the light was hitting this sided mirror here, and then was reflected to the reflected mirrors and coming back to the sided mirror. And on the same time, what was happening with the sided mirror was rotated, so that the genesis of this experiment was that the time that it took light to go from the sided mirror to the reflected mirror and come back to the reflected mirror, the reflected mirror has to rotate so that when it is coming here, it will hit the same side. So if this is side 1 and it is rotating, then when it is coming here before the observer sees it, will be hitting this side here, will be side 1 as well, the same side that the mirror was hit from the light source. So in this way, what is happening is that knowing the frequency of the rotation, then what is it? The sided mirror is serving the purpose of a timer. Okay, so what happened on this case is that the time to the rotation, so the speed of light is equal to 2 times the distance between the two mounts, on this case, between the sided mirror and the reflected mirror, times frequency of the rotation times the number of sides that each of the or this sided mirror has. So this formula is not in your formula sheet, but I will explain it to you why and how. So this 2 here is because the light is traveling, in this case, from Mount Wilson to Mount Baldy and then back to Mount Wilson when the observer is. N is, so this is 2D. N is the sides of mirror, so they are rotating, and then the frequency is the frequency of the rotation of the mirrors. So if we have an example, or if we have a problem that is dealing with the Michelson experiment, then you will see something like this, that in a Michelson type experiment, a rotated 8-sided, so 8-sided mirror was placed 50 kilometers away from the reflected mirror. The observer found that in order to observe the rotating, the returning light, the mirror should have be rotated with a frequency of, let's say, 375 hertz. What is the experimental value of the speed of light? So what do you do is you can apply the formula immediately. However, if you want to know why those formulas are in place, then you can calculate the period. So period will be 1 over frequency. And then from there, you can say that the time that it is needed to move will be whatever is the number of the sides near. So will be 1/8 of the period. And then the velocity, which is the experimental value of the speed of light, will be delta d over delta t. Delta d will be 2 times because it is moving from the side to the reflected mirror and coming back to the side. So it will be 2 times d. Convert this into meters over the time, this time here. And then you can go straight as speed. The experimental value of the speed of light is 2 times d times f times n, and that will be 2 times 50 times 10 to the power of 3 to convert it into meters times 375 times 8. And enter this in your calculator and tell me what your result. And you will have exactly as 3.0 times 10 to the power of 8 meters per second for this experimental value of the speed of light, which means that you are very good in those calculations and designing this experiment. Okay, so now let's move on and talk about the reflection. The phenomena of reflection is managed by that is known as the law of reflection. And the law of reflection is saying that the angle of incident is equal to the angle of reflection. But let's see now what is the angle of incident and what is the angle of reflection. Let's suppose that we have a surface, a flat surface that looks like this. And we have an incident ray that is creating with the perpendicular to the surface, so normal to the surface. An angle, and this is the incident angle. And then what this law is saying, that will be reflected. This is the reflected ray, and the angle of reflection is the same. So angle of incident is equal to the angle of reflection. Now you may say, why is those arrays here are just the way that they are propagating, the light is propagating. And you may say, why is perpendicular to the normal? Because every surface in mathematics and higher mathematics is identified with a vector that is perpendicular to the surface. So the surface is not the surface as what is the horizontal, but it is the surface as a vector that is perpendicular to the surface. Okay. Now, what you have to keep in mind is that if the angle with the surface is given, that is not the angle, the incident angle. So if we have a situation that we have a surface like this and the incident ray is like this, and I'm telling you that this angle here is 25 degrees. This is not the incident angle, because the incident angle is the angle formed with the perpendicular. So it is this one here. And then as a result of this, what we will have, we will see a reflected ray that is forming the same reflected angle as the incident angle. So now, keeping in mind that this is 90 degrees, so the incident angle will be 90 minus 25. So this will be 65 degrees, and so will be the reflected angle. And if we know the angle between the two rays, and we are looking for, so reflected and incident ray, and we know that this one here is, let's say, 170 degrees, then the incident ray that is equal to the reflected ray will be 160 degrees divided by 2, or 80 degrees. And if we have surfaces that are creating a certain angle with each other, so let's say that we have two surfaces here that are forming a 100-degree angle, and then the incident ray on surface 1 it's coming like this, and the angle with the surface is, let's say, 30 degrees. So we'll draw perpendicular here and then find this incident angle that is equal to 90 minus 30 degrees equal to 60 degrees. So will be the reflected angle based on the law of reflection at 60 degrees, which will leave this angle as 30 degrees. And now on this triangle here, the sum of inside angles in a triangle is equal to 180 degrees, telling us that this angle is 50 degrees. So we draw perpendicular here. Then the incident angle in the second mirror will be 90 minus 50, which is equal to 40 degrees. So will be the reflected, or the incident or reflected angle. So this will be 40 degrees as well, leaving this as 50 degrees. So the path that the ray will, as it is entering into this double mirrors here, will be starting here and then hitting the first one, moving to the second one, and then going away, reflected away from the second mirror. So this is the reflection. We will see some questions on it. I will give you some questions to practice and observe it. But we'll stop the video here for now because we'll move to refraction and then on and on.